recorder. The recorder is on. Today we're going to start a new module. This is the actual assembly language programming part of it, of this particular course, because this course actually has computer organization, which is the earlier part, and then also assembly language programming, which is what this part is about. But there's definitely continuity because we're going to use TTP, text toy processor, as the platform to run the programs. So there's continuity with the previous half of this class. So at this point, we're going to talk about a little bit about how to compile your programs, and that is in this particular module. I just recently moved it into GitHub, but the content has not been changed. It's still the same content if you have printed out an earlier version before. So this starts off with a discussion of C control structures, particularly the conditional statements. So if I were to show you this code here, okay, if A is less than B, A plus plus, B minus minus, according to the indentation, most people would think that B minus minus is a part of the then portion of the conditional statement, but it is not true. Okay, in C++, A plus plus in this case, as a statement, is the only thing that is in the then portion of the conditional statement. B minus minus is actually outside of the conditional statement entirely. Okay, so in Python, this is interpreted differently because Python is indentation oriented, which means the indentation tells you the nesting, but in C++, that is not the case. So this is important because in the following code, we make use of the C++ convention of using conditional statements. So understanding why B minus minus is not a part of the then statement is actually essential to understand the rest of today's, some of today's lecture. So the reason why that is the case is from the compiler's perspective. As soon as the compiler sees the keyword if, it will expect a parenthesized condition, which is this expression here. Right after that, it will expect a then statement, and I mean a single then statement. So in this case, A++ with a semicolon is a single statement, and that meets the requirement of, oh, I'm supposed to see a then statement. And then after that point, okay, when the compiler is done with parsing this particular statement, then it will say, okay, I can optionally expect a keyword of else, in which case there's an else branch. Or otherwise, I'm ending the conditional statement. So in this case, because the next thing is not an else, so that means the compiler decides I'm going to end the else state. I'm going to end the conditional statement, which means B minus minus with a semicolon has absolutely nothing to do with the conditional statement itself. All right, so this is important. Okay, do we have any questions about what I just said? No questions. All right. So if there are no questions, we are going to move on to the actual, the actual portion of this lecture, which is, this is structured programming because we have a conditional statement on the outside, and then block one can be whatever it needs to be. In other words, block one, BLK1, can be a while loop, it can be a do while loop, can be another conditional statement. We don't know what it is, nor do we care what it is. Okay, but this is structured programming because structured programming allows one statement to contain another statement, and that's the whole concept that I'm illustrating here. Same thing with block two. Block two is just a block of code to execute if and only if the condition C is false in this block, in this entire conditional statement. So do we have any questions about what a conditional statement looks like and what it does in C++? Okay, I don't see any questions. So now here comes the fun part. The fun part is this code here, which is structured programming because of the use of block statement, curly braces, can be translated into this statement here where the curly braces are all gone because they are not necessary anymore. So in this case, we want to say, okay, are we really going to execute block one if and only if C is true? Well, If C is true, then not C is going to be false. If not C is false, the then statement corresponding to this if is not going to execute. So that means if we fall through to block one, block one has a go to L1 right after that, which goes to this label, which is a continuation label, which means we're not going to perform block two after block one, and that is the correct behavior in a conditional statement. What if C is false? If and only if C is false, we should execute block two. So if C is false, then not C is going to be true. In that case, the condition is true. So the conditional statement will execute its then statement, which is a single go-to statement. Go to L1 is basically the same thing as JMPI in assembly language, in our assembly language. So this will just continue execution at the label L1, which is right here. Then it will execute block two. Block two will fall through to L2, which is also marking the end of the entire statement. So in other words, by performing that analysis, I have just established that what looks like this in a traditional C++ program can be translated into something like this, where there is no need for the braces anymore. There's no need for nesting anymore. Do we have any questions about the equivalency between these two forms of conditional statements? So you might be asking, but why are we doing this? Okay, I thought structured programming is a good thing. Well, it is, except it doesn't exist in assembly language programming. The assembly language does not have blocks. It does not have braces. It does not give you any syntactical construct so that you can do nesting. So that's why we have to basically get rid of all the structure in structured programming. We are basically deconstructing programs in this case. So in the case that there's no else, then it's a little bit simpler. So for something that looks like this, it just translates into something like this, which is basically saying if the condition is false, let's just continue at label L1 and skip over block one, which does exactly the same logic as the original statement. Are we good so far? All right, moving on to pre-checking loop, which is what most people call this a while loop, but because in C there's also do while, I call this pre-checking loop because that's exactly what it does. It checks the condition before executing the body of the loop. So this is the typical way for people to write a while loop. There's a condition to evaluate, and then there's also a block of statement to execute for each iteration. So the key here is we need a label L1 before everything else, because this is where we need to go back to after each iteration. So there's an unconditional go to go back to label L1 so that we can repeat the operation. The important part here is there's a conditional statement here that says if not C, this is C and this is the negation of that. If C is not true, let's go to L2. L2, once again, is a continuation label, which basically just says, oh, okay, we're done with this loop. Let's just continue with whatever is after the loop. If C is true, then not C is going to be false. If not C is false, then we are not going to execute the then statement of the conditional statement, which means we just fall through to execute block one. After block one, we fall through to the go to L1 here, and that just goes back to the label L1 and continue with the next iteration of the loop, which starts with checking the condition first. So do we have any questions about the translation of the while loop into something that does not even have a while in it? It just has go-tos, labels, and condition, a condition. So are we good with that? Okay, all right. So now we move on to the post-checking loop, which is only the last of the loops. I'm not going to translate for loops because a for loop is really just a while loop, except the initialization is before, it's also included into the parentheses, and then the post operation is also a part of the parentheses. But other than syntactical aspects, a for loop can be translated into a while loop, and that's why I'm not including the discussion of a for loop in here. A do while loop is actually the easiest one to translate. it translates to, starting with a label, because I need a label here so that I can go back to that label. We perform block one first because it's a post-checking loop. That means that we check the condition only after the body of block one executes. In that case, we say if C go to label L1, because C is a condition that needs to be true in order for me to start the next iteration. So do we have any questions about the post checking loop? Nope. All right. All right. So if there are no questions, we are going on to the next section, which is basically saying, okay, if we repeat doing this, okay, if we repeat these operations, then eventually we'll boil everything down to just if something go to. There won't be any uh, there won't be any braces left in the program. Okay. So just to illustrate what I mean by that, I'm going to work with an example in this class so that we can check out how to apply these techniques. All right, so I am going to, okay, so I'm gonna remove, oh, okay, I cannot do that because I did that yesterday. So today I'm gonna do a min3 program here. This is the block of C code is not a complete program. So we have integers A, B, C, and D. The purpose of this program is find the minimum of A, B, C, and store that in the variable D. All right, so there are a few ways to do this. I am going to do this in a nested conditional statement. So I'm going to say if A is less than or equal to B, then we do something here, else we do something here. So it's a very simple comparison, and let me change this to greater than or equal to. Okay, just so that later on, it makes a certain thing easier to do later on. All right, so when we get into here, we can confirm that at this point we know that A is greater than or equal to B, which means B can be a minimum, but we have to compare that to C in order to find out. So now we say, okay, let's compare B with C. If B is greater than or equal to C, then we come to one conclusion. Otherwise, we come to another conclusion here. So at this point, what do we know? At this point, we know that A is greater than or equal to B, and we also know that B is greater than or equal to C. That has to do with the structure of the conditional statement. So this part has nothing, absolutely nothing to do with assembly language programming, but it has everything to do with CISP 300 and CISP 360. If I have to choose, I'm going to say it has everything to do with CISP 300 more so than CISP 360, because 360 just introduces the syntax of C, but the concept should have been introduced in 300 already. All right, so what do we do? Well, that kind of tells me that C is legitimately the minimum in this case. Now, the question is, can A, B, and C all be the same? Yes, they can all be the same. But even in that case, I can still say that C is the minimum in this case. Does that make sense? Okay, so that means I can now conclude and say, okay, let's store the minimum into variable D. What does it mean when we get here? Well, A is still greater than or equal to B, but at the same time, we know that B is less than C. So in this case, we can see that B is probably the minimum. So D is equal to B in this case. Well, in fact, we know that B is the minimum because B is no more than A, but B is also less than C. That makes B the minimum. Is that okay so far? Okay. So what about the else? Well, the else here means the condition of line 3 being is false. So that means A is known to be less than B by the time we get here. So now we go like, okay, I know A is possible as a minimum, but I cannot know for sure until I compare A versus C. So now I compare those two. So you can either do A is greater than or equal to C, or C is greater than or equal to A. It doesn't matter. Okay, either way, I will get all the information that I need. So here, we know that A is less than B, and we also know that A is less than C in this case. So that means A is the minimum of the three, B equals to A. And then over here, we know that A is less than B, and A is, oh, I take it back. Sorry, that was my bad. In the previous one, A is greater than or equal to C. So that means, wait, okay, does that make sense? A is less than B, so A is legitimate, and then C is the minimum in this case. Because the other way to rewrite this is to say A is greater than or equal to C, but B is greater than A. So if you look at it this way, then we can establish that C is the minimum. Okay, that was my bad. So now we know A is less than B and A is less than C. So now we know that A is the minimum in this case. All right, so this code is all done in C. You can, once you put this code into an actual main function, you can actually debug it and test to see whether it works or not. So let's just assume that it works. Okay, now we need to convert it into assembly language using what has been introduced already. So let's do that. So now we look at this and go like, okay, so line 3, marks the beginning of the outermost conditional statement, which makes line 5 all the way to line 15 block 1. And then from line 19 all the way to line 29 is block 2. Is that okay? So as far as I'm concerned, I'm not touching those lines, okay? Because I don't need to. So what I really need to do is to change the beginning of is to change these lines. So I'm going to comment here. Okay, before we do that, I'm going to save this file, and I'll save it to a new file called min3a.c. So by the end of this lecture, there will be like a bunch of files, each one representing one kind of change to the original file. All right, so we're going to comment this out because we are basically doing what the transformation is supposed to do. We are removing the structure of the entire program. But in this case, we are only applying to the outermost conditional statement. So we replace this with saying, what if it is not the case that A is greater than or equal to B? If that is the case, go to a particular label. In this one, I am going to use L1, L2, L3, L4, okay, just to illustrate how confusing it can get at some point in time. So this L1 is corresponding to the else of the outermost conditional statement. So L1 needs to be defined here. But I also need to remember to have a go to here to go to the continuation label, which is which I'll call L2. Just sequentially, I'm naming my labels. So L2 has to be defined here. Okay. So now I believe this is all done, okay? Because I converted the conditional statement that has an else part into a conditional branch like this with a go to at the end of block 1, and then a label to start the else statement, and then a continuation label defined at the very end of the original conditional statement. All right, save that again. But I'm not done yet because there are nested conditional statement here. So I need to now do the same thing to the nested conditional statement. So I'm gonna write this one as min3b this time. So this way there's a sequence of files that you can look through in order to see what I have done for each one. So we'll now work with min3c. Okay, let me just double check. 3b, sorry, this is 3b, that's min 3a, 3b. So this is 3b. All right, so let's work on the innermost, the inner conditional statement. So now I'm looking at the conditional statement starting on line 7 and ending on line 16. In that case, block 1 is from line 8 to line 11. Block 2 is from line 13 to line 16. But I can apply the same technique. So I can now say, okay, let's comment out everything that is quote-unquote structured for this particular conditional statement, and then replace that with the code that we are supposed to be using. So now we say, okay, give me a reason to go to the else statement. So we are looking for the negation of the original condition, and then we go to, oh, I cannot use L1 anymore, can I? Right? Because L1 already has a purpose. L1 is the label of the else block of the outer conditional statement. So now I have to remember L1 and L2 are both used. I have to use L3 now. Okay, you can see how this can be a problem because if you accidentally use L1 here, the compiler says it's okay, not a problem because L1 as a label is defined. Okay, so we can kind of see that this can potentially lead to some problems later on. So L3 is going to be defined here because it is supposed to be the beginning of the else block. But I also have to remember to go to L4 now because L4 is the continuation label of the inner conditional statement. So L4 technically is belonging here. Now, if you say that, oh, but we can just go straight to L2, that is correct, but only in this case. It's only because there are no additional statements after the nested conditional statement. But if there were any additional statements after the inner conditional statement, then you cannot shortcut this anymore. So I'm not going to concerned about, in this class, I'm not concerned about efficiency or an optimization. I'm just going to do it this way. It is the most systematic way to do it, which means it is the least likely method to introduce errors. So now I'm going to do the same thing with this conditional statement. So line 27 to line 36 is also a conditional statement. It has an else portion in it. So I'm going to apply the same technique that we were talking about before. Okay, so now we comment out everything that is structured about this, and then we just convert that into something that is not structured. So now we look at the negation of the original condition, which is just the negation of A is greater than C. But this time we have to go to another else label. Let me see. 1, 2, 3, 4 are all used. Now we have to go to L5. So L5 is the label starting the else branch of this particular conditional statement. So this is where L5 is supposed to be defined. And then I have to go back to here because after block 1, I have to go to the continuation label of this particular conditional statement, which is going to be L6. L6. And then L6 needs to be defined right here, which is at the end of this conditional statement. This is where L6 is located. Now you will see that L6 and L2 are sequential, which means they really are defined to be the same location. Okay, if you want optimization, there is no need to define L6. But L6 really does not take up any execution time because it's just an additional label. So by the time this program or the compiler in this case is done with this code, it doesn't really hurt anything. So I still prefer to do it like this and not to do the mental optimization of, oh, but L6 and L2 are the same thing. We don't have to define L6. Whenever we go to L6, we just say we go to L2. Yes, you can do that, but I wouldn't do it. Okay, because I like things to be structured. I like things to be systematic. So even though it uses up one more label, it's not a big deal. Okay, so now we are this is this is still a C program, okay? Which means this will still compile in a C compiler. Now, when I say C, I really meant C/C++ because I'm only using a subset of C++ that is called C because the C programming language predates C++, and I only use that particular subset in this class. So for anyone who's thinking, but I haven't learned C, yes, you have, okay, because C is a subset of C++. All right, so now we look at this and go like, this doesn't look like assembly language to me. Nope, it's not. This looks like C code to me. Yes, it is. It just looks ugly. Okay, can I still use online GDB or CodeBlocks or VS Code to debug this program? Yes. It should still behave exactly the same way as the original program. Okay, so if I were to, save this file, go back to min3.c, this original code that looks kind of pretty versus this code here that looks absolutely ugly, they still mean exactly the same thing, which means you can still debug it, you can still run through the same test cases to make sure that the program behaves the same way, even though it looks different. Is that okay? All right. But at this point, we go like, how are we going to proceed at this point? Because we have comparisons, we have the use of Boolean operator, and then we have these assignment operations and whatnot. Well, that's why we need to look a little bit further in today's note to find out, at least how to deal with the negation of something. Okay, and then we will talk about the other Boolean operators as well. So the Boolean operators are discussed down here. Okay, so if you have something that looks like this originally, we can translate it into something like this. The idea is to get rid of Boolean operators in a condition. So in the original one, we have a negation here, and then we say, oh, but we don't want the condition to be negated because we want the condition to be as simple as possible. Now, what is simple in this case? It only consists of comparisons that we can do in TTP. Okay, that's what I mean by simple. Negation is not one of the things that we can do in assembly language. Yes, there is a not opcode, but the not opcode is a bitwise not opcode. It is not logical not. Okay, so it doesn't mean the same thing. Okay, so does this block of code, which looks absolutely ugly, do the same thing as this block over here? Well, let's check it out. So in the original code, I would go to label L1 if and only if C is false. Because in that case, if C is false, not C is true, then we execute the then statement of the conditional statement. If C is true to begin with, we simply fall through to whatever is after this conditional statement. So we want to preserve that behavior. In the second block of code, if C is false, then we are not going to label L2, which means we fall through to go to L1, which means, we end up at label L1. But what if C is true? Well, if C is true, then we execute the then statement corresponding to the conditional statement. Then we end up at label L2, which is simply continuing with whatever is next. It does not go to label L1. So that means I have also just shown you that these two blocks of code are equivalent in terms of whether we get or under what condition do we get to label L1. Okay, but the nice thing is we are getting rid of the Boolean operator here. We're simplifying the condition by complicating the control structure. Is that okay? All right, which is kind of what we are going to do from here on. Okay, we are reducing the complexity of a condition or Boolean expression by complicating the control structure. So the next one is about the OR. Okay, so let's take a look at the original one. So what if we have C or D? Now, C by itself can be a gigantic expression. D by itself can also be a gigantic expression. We don't care, okay, because we are only reducing the complexity one step at a time. Okay, so this technique has to be repeatedly applied until we boil everything down to simple comparisons that can be done using text-to-processor or whatever architecture you choose to use. All right, so C or D. So that means if at least one of these two is true, we should end up at label L1. So the translation of this one turns out to be one of the easiest because we say, hey, if C is true, let's go to L1 already. We don't have to take a look at condition D because in a disjunction, if at least one side is true, the whole thing is going to be true. Okay, if C is true already, I don't care about D. I just go straight to label L1. Does that make sense to you? Okay. Well, what if C is not true? If C is false, I cannot execute the then statement of the first conditional statement. So I'm going to fall down to the next conditional statement. And at that point, I evaluate D. If D is true, I still have a second chance to go to label L1. But if both C and D are false, sorry, I just have to continue execution with whatever is after both of these conditional statements. Does that make sense to you? Okay, so this is also why we have short-circuited Boolean expression evaluation, or otherwise known as lazy evaluation. How many people have come across that term before CISP 310? Really? Or are you guys just shy? Nobody has been introduced to the term called lazy evaluation or short-circuited evaluation. Okay, well, in that case, I'm gonna introduce that concept. This is telling you exactly what is going on when we short-circuit the evaluation, because the original expression says, okay, give me C, give me D, and then I'll evaluate the disjunction. Okay, which means C and D are both evaluated without the lazy approach. The lazy approach says, hey, if C is already true, we don't have to bother with D. Okay, we just say that the whole expression is true. Let's just go to label L1. That is why it is called, quote unquote, short-circuited Boolean evaluation, or you can also call it lazy Boolean expression evaluation. All right? But with this, it means the ordering is important, okay? Because with, okay, let's just say that we have C times D, okay? C being an integer, D being an integer. In a multiplication, the compiler can actually choose to evaluate the right-hand side first or the left-hand side first. The ordering of the evaluation of an expression that has two operands is up to the compiler to decide. It is not specified in the programming language specification itself, unless you're dealing with a logical operator like this or this, then it has to evaluate from left to right because of short-circuited evaluation. This particular short-circuited evaluation approach is also used a lot to simplify the logic of a program. I'll show you one example after we talk about the AND short-circuited evaluation. So now we move on to the last logical operator, which is AND. So if the original expression has C and D, now once again, C itself can be very complicated. D itself can also be complicated. We are only working to remove one operator at a time. So if this is the original thing, then it becomes something like this. If not C, go to label L2, which is a continuation label. Otherwise, continue with the second conditional statement. If C is true, we move on to the second conditional statement, where we evaluate D. If D is also true at this point, then we go to label L1. So the question is, does this work the same way as the original one? In the original one, the only time I should go to label L1 is C is true and D is true. Okay? For all other cases, I should just continue with whatever is next to the conditional statement. So the second block of code, if C is true, then not C is going to be false. We are not going to label L2. We will drop down to the second conditional statement, and then it would say, it would check whether D is true. If C is true and D is also true, that is the only time we go to label L1. Because if C is true but D is false, sorry, we're still continuing at label L2, which is just a continuation label. But what if C itself is false? Well, that's even easier. Because if C is false, not C is going to be true, we just go straight to label L2 without even evaluating condition D. So once again, we have short-circuited evaluation here. So I'm going to throw a bonus into this class, okay? Because so many of you did not, told me that you have not been introduced to short-circuited evaluation. So I'm going to show you an algorithm that that is best implemented with this short-circuited evaluation, meaning that you can do the same thing without this feature, but your program will look more clumsy, and you will have to use one more variable in the process. Okay, so let's just say that we let A be an array with n elements. We want to see if k is a value in array A. Okay, so this is what we want to do. So in your CISP 300 or 360 class, they probably have talked about how to search in an array to confirm whether a particular value is in the array. Is that correct? Okay, I see a bunch of dots. Okay, very good. So I'm not sure what algorithm your professor taught you, in CISP 300 and CISP 360, but this is the algorithm that I would use. Okay, I'm going to say while blah blah. Okay, and then with the while loop, it has both of these components. So there are two things I need to check in the while loop. The first one is, am I at the end of the array already? Because if I'm already at the end of the array, I should just exit. Okay, so we'll also use int I as the index into the array. So the first thing is, well, most people know this, I needs to be initialized to 0 because that's the index of the first element in the array. So I'm just going to work on this step by step. Okay, so I'm not going to save the file multiple times. So if you want to record the process of working on this code, you would have to replay the video and then jot down some notes. But it's not really a key part of this class, so I don't think you really have to write it down, okay? But it's something that is helpful to you to know. So I'm gonna say if I is still a valid index and a bracket I does not match k, only in that case I want to perform I++, which is let's take on the next element. Does that make sense? Okay. So now the question is, how do we do this? Well, first of all, there's no and. There's only ampersand, ampersand. That's an easy one. Does not match. That sounds like not equal to me. Easy change. So now we have to say, okay, how do we know that I is still a valid index? If the array only has n elements, I need I to be less than n at all times. Okay? And if the function needs to return true if and only if the element is found, I can just return I is less than n after the loop. Because I is less than n can only be true if I exit the loop because a bracket I does not equal to k is false, which means I found a match. Does that make sense? So is this the actual algorithm that you were taught in CISP 300 and 360? No? So what type of algorithm did they use? Say again?
For-based searching. So they have the max array as a conditional. So like for I, int I equals 0, I is less than array.length,
Mm-hmm.
and then I++, and then just have a temporary sign then to find the match.
So you have one more variable to check whether you have found the element. Okay. But this way, you don't need that extra variable. Because in this case, I is less than n is called a guard condition. So the guard condition says, if I is less than n is false, don't even bother to access element I of A, because in that case, there's no such thing as element I of A if I is not less than n. Okay, but to make this work, it relies on short-circuited evaluation. Because if I is less than n, it would go ahead and do this, and it is safe to do so whenever I is less than n, assuming I is not negative. But if I is not less than n, meaning I is greater than or equal to n, this is not safe to do anymore because that element does not exist anymore. Now, is it bad to read a location where it does not correspond to an array item, in the array? Not necessarily, okay? But it's still not a good thing to do. Okay, so this is kind of one application of short-circuited Boolean evaluation, because without this, you will need to complicate the program a little bit by introducing an additional variable, because the only condition you have to put in the loop here is just whether I is less than n, and then you have to also end it with another variable here, and that one has to be initialized, has to be updated in the loop. It makes things a lot more complicated than what it looks here. So we okay so far with this example. Okay, all right. And once again, if you're not fully grasping this example, it's okay in assembly language programming as a class. But I'm just telling you that this is the mechanism of why we have short-circuited Boolean evaluation. All right, so with that said, there are also other things that we can do simple stuff. Like in this case, we have the negation of x is greater than or equal to y. That's just x is less than y. If you, excuse me, if you have x is less than y or x is greater than y, we can rewrite it as x does not equal to y. Okay. So now we basically say, oh, okay, so we now have the mechanism to boil everything down to just comparisons. Okay, because if in the center of every condition that you write in C++ or any other programming language, there's usually some kind of comparison. Okay, so now the question is, what kind of comparison can we perform using the using TTP, using text toy processor? So you think about the 5 flags that we have. Can someone name the 5 flags in the flags register?
The register, the LNU.
Hmm?
The register, the LNU.
Inside the ALU, yes. Inside the ALU, yeah, but also each one has a name. We introduced the conditional branch instructions already. There are 5 of them. So name the 5 conditional branch instructions. You just use those 5 in a horrendous, lab, where you have to run the code like multiple times, and then every time it runs, you have to count the number of times you get through a certain no-op instruction. Remember that one? I hope so, because we did it on Monday. Okay. So with that one, can someone tell me which 5 conditional statements we were working with? All right. Okay. So this means, we might need more reviewing, okay, of these topics, because this is actually important. There's JCI, JZI, JSI, JOI, and then JLI. Okay, those are the 5 conditional branch instructions. Each one is looking at a specific flag or each one specific bit inside the flags register. Well, guess what the names are for those particular bits? C, Z, S, O, and L. I believe the same lab also had an example where I gave you like an 8-bit number, either plus or minus another 8-bit number, and you have to tell me the values of the 5 bits. Same 5 bits. So after a subtraction, okay, which can be coming from a compare or an actual subtraction instruction, which ones do you think is related to determining whether the first thing is less than the second thing or they are the same? C is one of those, okay? The C flag is true if and only if the x is less than y after a binary subtraction. So like, when did we talk about that? When we talked about binary comparison, okay? Because the C flag, which is normally known as the carry flag, it is also the borrow flag, okay? Because of how the ALU arranges things in the inside, the C flag is also the borrow flag. The borrow flag is the same as T8 for 8-bit subtraction. So that is something that we talked about in binary comparison. So if you cannot remember those things, you might want to jot down in your notes that you need to go back and review binary comparison, which depends on binary subtraction. Okay. This is also useful, okay, because the Z flag is a 1 if and only if the result of a subtraction is a 0. In fact, it's a 1 if and only if any operation ends up with a result of 0. Okay, so I would say the Z flag is useful. The sign flag is not particularly useful because the sign flag is only useful for signed numbers. But after a subtraction, the difference can be out of range, which means there's an overflow. So looking at just the sign flag alone cannot tell you whether x is less than y. We have to look at both the sign flag of the difference and also whether there's an overflow in order to determine whether the first operand, which is x, is less than the second operand, which is y. So that means L is also useful after a comparison because the L flag is a 1 if and only if the signed value of x is less than the signed value of y. And it will tell you that reliably. The sign flag alone will tell you the truth sometimes. Okay, it needs the overflow flag to also kind of handle the other part. So all of this is from binary comparison. Okay, so if you think you're getting a little rusty on these concepts, it is a good idea to go back and review that particular module. Okay. I think the main difficulty of this class, other than you having me teaching this, has to do with the complexity and the number of concepts that you have to keep track of and also relate. Okay, so because if you're not relating the concepts, then you're not getting the actual content of this class. Okay, it is about the connection of the concepts. Each individual concept is useful, but they're much more useful once you see how they all relate to each other. And this class, compared to even CISP 440, has a lot more. When you look at how far the connections go, I think this class exceeds 440. 440 is a math class. I mean, there are some dependencies in that class, but when you look at the hops of the concepts, there are only the hops of this class can far outweigh can be much longer compared to 440, and that's the difficulty of this class. Which also means notes, taking notes and reviewing your notes, and also constantly thinking how does this relate to things that we have learned up to this point. That is also important, much more important in this class than many of your other classes where there's not a long dependency of your concepts. All right, so it boils down to this. Okay, it boils down to, after a comparison, I only need to know whether the first thing or the left-hand side is less than or equal to the right-hand side. If I can do one of these two things, I can handle the rest. So x is less than y, not a problem, because once again, if we can handle less than, this can be handled. Greater than, not a problem, because we can just flip the ordering of the operators. So if the original expression is x is greater than y, we can flip it to become just y is less than x. X is less than or equal to y can be boiled down to x is less than y or x equals to y. Okay. X is greater than or equal to y can also be boiled down by reversing the order of the comparison. So that's an easy one. X equals y, we can handle it. The z flag is what we use to handle x equals y. We can confirm whether x and y are the same after x minus y by looking at the z flag. X does not equal to y is, well, this time we do need a negation. It is a negation of x equals to y. Are we doing okay so far with these comparisons and how I can transform one of the well-known relational operator, which is comparing, to things that we are allowed to do, being just less than and checking, confirming whether there's a less than and confirming whether there's a equal to. So we doing okay so far? Okay. So now we look at the general compare, okay? Because by the time you're done with getting rid of all the Boolean operators, what should remain are just comparisons, okay? So now the question is, if I have x, r, y, r being either less than or equal to, how do I translate that into assembly code? This is the first time in the entire module here that we actually have to deal with TTPASM. TTPASM, somebody asked me yesterday in the Tuesday, Thursday class. What is TTPASM? It stands for Text Toy Processor Assembly Language. Okay, so in this case, the first thing you need to do is to compare the two values, x and y, and then after the comparison, the flags will be set. In other words, all 5 flags will be affected by a CMP, a compare instruction. At that point, you can choose the one that you want to look at and then use it for branching purposes. So that means in this case, assuming that X and Y are unsigned, if you want to implement something like this in the original C code, it translates to this assembly code. Assuming X is already in the register, Y is already in the register, you say compare XY, and then the C is what we use because it is there because X and Y are unsigned. If X and Y are signed, then we use the L flag. Is that okay? In, uh, this is all here, okay? They're in the notes already in the module that I have written, but it does not hurt if you keep track of your own notes and organize it in your own way, okay? Because the way it is organized here is following the logic and the flow of explanation, but it is not summarized, okay? It is not condensed into a nice little table so you can easily look it up and go like, oh, okay, I know what to do in this case. This is following a logical explanation of the concept. So the flow is only for that purpose. It is not for the purpose of, I need to find that information really quickly. Nope, this is not intended for that. Okay, so if you want to make sure that you can find the relevant information quickly, both for the purposes of studying and also for the next exam, what do you need to do? You can write your own notes, okay? You move things around until it is the way that you like to organize things. And everybody has a different way of how you want to organize. Okay? If you're not one of those people and go like, I want to just kind of print this out, okay? Well, that's fine. You can use a highlighter, okay, and highlight the portions that you think is useful or is important. Okay? But there are things that I just talked about that is not in this note. Okay? Namely, how this particular module is related to binary comparison. Okay, that's a connection that is not that I didn't quite mention here, but that connection is nonetheless important. All right. So the next section here, I mean, as far as translating a program directly into TTPASM, we are done, okay? And we're only about 1/3 through the notes. Then you'll be asking, what about the rest? Well, the rest has to do with programming style, okay? Which means how do I name the labels, okay? How do I work on this program? Should I work my code from the outside in or from the inside out? A lot of that is personal. It's kind of subjective. You can do whatever you want, okay? I just have my own way of doing things that is systematic. But let's go back to the example that we saw earlier, not this one. Okay, we're going to look at min3 b of c dot c. Oh, that's b. Okay, there we go. And now we're going to translate into assembly language. So I'm going to save the file again. This time it's min3 .ttpasm. Okay, I use the extension of ttpasm just to make sure that I know that I can remember that this is in text toy processor assembly language. There is no such thing as declaring integers, okay, because A, B, C, and D are integer. I mean, they are registers. So now I look at these and I go like, okay, we can simplify this. Get rid of the not and turn this into less than. Take out the not, turn this into less than. Okay, the extra parentheses can go away too. And then over here, same thing, get rid of the not, turn the greater than or equal to a less than, get rid of the extra parentheses. Are we doing okay so far? So this is just a simplification. If you can simplify a negation so that it becomes something simpler without having to complicate the control flow, do it that way. Okay, you just save yourself some time by doing it like this. Okay, so now I've done all that. So now I look at all the conditions that I need to evaluate. Okay, this is just a less than. Looks like we can convert this directly into assembly code now. Okay, indeed we can. So now we look at this and go like, let's convert it into assembly code. The assembly code, according to the notes here, now this is the other thing that is going to be helpful is reading the notes ahead of time or having the notes in front of you on your own computer or printed out so that you don't so that I can flip-flop between the screens, but if you have it open in front of you, then you can basically keep it at that point and you can focus on just the code that I'm writing. So this particular template translates into this particular template here. So I go like, okay, I'm seeing that template in my own code because the R is a less than, I can deal with less than. So now we go, I look at this and go like, okay, we compare A, B, and then J, in this case, because we are dealing with signed integers, is JLI to label L1. And then here, kind of the same deal, except just two different registers. So compare BC, JLI to label L3 here, and then over here, same thing, okay? Compare AC, JMPI to label, oh, no, nope, oh, I just made a mistake. JLI to label L5, okay? In other words, it is a matter of matching which template is applicable and then apply it. Are we good so far? What about the rest of the program? It's not too bad. The rest of the program is actually fairly easy to do. There's no such thing as an assignment expression in assembly language, but there is something that can do this, okay? Now, we haven't really talked about that specific opcode, so let me see if you guys can help me find the opcode or the instruction that can do this from the opcode table. So let me see. Yeah, go ahead. CPR, that's right. Okay, so CPR is doing exactly what we need to do, which is copying the content of one register to another register. Okay, what about LD? Isn't LD doing the same thing? Well, okay, let's take a look at LD and you guys can tell me whether it is the same or not. So where is LD? LD is right here. So we are comparing this to this. Are they the same? Dereference. Yes, that's okay. I know what you mean. Yeah. One is a dereference, which makes these two entirely different. Because one is saying, oh, whatever this register has, we'll just copy that to the other register. That is CPR, copy register. The other one says, okay, we'll take one register, go to where that register is pointing to in RAM, grab that content in RAM, and then copy that content of RAM to the other register. Okay, so that's an entirely different operation. So for the same reason, we can also say, okay, what about this one compared to store? Because store looks like we got X and Y and there's an assignment operator. Well, that is also entirely different because in the case of store, we are storing a register to not the other register, but what the other register is pointing to in RAM. Okay, so it is very important not to confuse between these three instructions, LD, ST, and CPR. They are meant for doing entirely different things. Okay. All right. So now that we know it's a CPR that can get the job done in our case, now we can go back here and go like, oh, okay, I can do this. CPR DC. And then over here, CPR DB. Okay. And then over here, CPR DC. And then there's one more. Okay, this one is CPR DA. Okay, and you can now start to see, uh, the order of the operand is following the left-hand side versus the right-hand side. In other words, if you're dealing with LD, ST, LDI, or CPR, or add, or subtract, or anything that has two operands, the first operand is always the one being changed. If any operand is getting changed, it's always the first one, because that's how C is specifying. C specifies which side of the equal is the one side that is getting changed. So there's consistency. Okay, I chose that order for a reason. All right, we are almost done. Okay, except for the go-tos. So what do you think we should use instead of go to L4? What should we use? not JRI. JRI says we are only it's a conditional jump. Is this conditional? Do we go to L4 for certain cases and not to go to L4 at certain other cases on line 17? This is not conditional. We're just jumping, and that would be
It says it over there, jump.
JMPI. Yes. All right, so that's a easy change, right? I mean, it's the same label here. We just have to change and go like this is JMPI to L4. I mean, if you're really good at working your editor, you can do all this without uh, relatively quickly because you're just replacing go-tos with JMPI. There's one more here. L2. Okay. I think that's it. This program would actually assemble and it would run. Is that okay? So this is a very short demonstration of a program that I wrote in C, or a piece of code that I wrote in C. I didn't finish the entire program. And basically, gradually, step by step, convert the program into TTPASM. The focus here is not about the assignment. The focus here is really just the control structure. How do we convert the control structure in C gradually to a flattened program, also written in C, so they can still debug it in the C compiler and debugger. And only the very last stage converts the whole thing into assembly language. In other words, I'm trying to defer I'm trying to defer the necessity to debug the program in TTP ASM as much as I can, so that you can use code blocks, you can use VS Code, you can use online GDB or any one of those tools to debug basically still a C program. It's just ugly. Are we doing okay so far at this point? Okay. So I am going to, what I'm going to do next is to talk a little bit about opcode hijacking, because that's what you need to know and actually understand in order to do today's lab. So we'll go ahead and talk about a few instructions. Okay, so I'm gonna, oh, okay, I just did some change here. Control Z. I want to undo this. Okay, undo. There we go. Okay. So I'm gonna go back to my editor, okay, and I will give you an example, okay? So I'll give you, okay, I just need to have a name here, hijack.txt. All right, so I'm gonna give you a few examples of things that are utterly useless, okay? CPRAA. Do you think this is a really useful operation? I'm just copying A to A. So it's not useful at all, okay? A few other ones can also be considered useless. Comparing A to A, would that be useful? In other words, is there anything of the result of comparing A to A that I cannot figure out ahead of time, not knowing the value of A?
They get this complicated, but I'm thinking that you can compare that if you alterated A at one point.
But would it actually change the flags after compare A to A? Exactly. So compare AA is also useless. Okay. So we go like, okay, there are a few other things that may be useless. What about AND AA versus OR AA? Okay. So these are bitwise operations. Basically I'm bitwise ANDing A with A, or I'm bitwise ORing A with A. Okay. So the question is, are these operations useless? Well, let's look at it from two different perspectives. The first perspective is any change going to happen to register A? To understand that, okay, we'll go ahead and I'm just going to use my text editor here to illustrate it. So let's assume that A has a particular value. So let's say it is 10010110, okay, for whatever purpose, okay? This is the value of A. I'm performing a bitwise AND with A, which is the same thing. And the result is every bit is storing the corresponding position or the result of the end of the corresponding position. In other words, in bit 0, I'm looking at what is 0 and 0. Okay, that's a 0. What is 1 and 1? That's a 1. What about 1 and 1? That's a 1. What about 0 and 0? That's a 0. What about 1 and 1? 0, 0, 0, 0, 1. You go like, wait. So we are not really doing anything. Okay, the result of the AND AA operation, A is not changed. That doesn't seem to be very useful. But does this operation go through the ALU? It does go through the ALU. Okay. Now, if you're not sure whether this instruction goes through the ALU, what do?
You can just check the process, see where it is, evaluate where's it going to.
So you basically go to the assembler, you specify AND AA, copy that opcode over to the first location in RAM of TTP in Logisim, and then you click Control T 4 times. So you would get right after decode and before execute. And then you track down where the registers are going. And then you will find the register A is both used to go to in1 and in2 of the ALU. And after the calculation, the output of the ALU goes back to the register bank to update register A. Then you go like, okay, great. So this is a scenic route of doing absolutely nothing because it doesn't do a single thing. A is not changed. However, okay, this part I have to graphically show you because I think it has more impact than me just kind of talking about it. So let me start up Logisim and load the processor. Actually, I can just load the ALU itself too, but I'm going to load the processor first. So we go to the ALU. I don't even need to be running the instruction. This is the output, okay, which is the result of A and A. Okay, it's going to be presented here. So you look at this and go like, wait, instead of just going to the output pin right here, there are two things that we are doing to every outcome out of the ALU. And what are those two things? Okay, just follow this note here. Where do they go? They go to the output pin. Okay, that's good. I mean, that's the actual result of the operation. But we also get to S out and eventually go to Z out. Z out is the Z flag. S out is the S flag. So that means the AND AA instruction, even though it doesn't do anything to register A, the value of register A stays the same, it will still influence the flags. That is important. Because that means after AND AA, okay, so let me go back to the example that we were working on before. So that means after this AND AA, two flags will be affected. The S flag is going to be affected. Can somebody tell me what the S flag is going to be in this case? So how do we relate this picture and the ALU that I was showing you earlier, specifically this part of the ALU? The result being 1 0 0 1 0 1 1 0 means it has 1 0 0 1 0 1 1 0 here. So what happens to the S flag? Is it a 0 or is it a 1? It has to be one of the two. It's going to be 1 because it is bit 7. Okay? What about the Z flag? Is it going to be a 0 or 1? This one here. We have basically 1 0 0 1 0 1 1 0 presented to the NOR gate. This is a NOR gate, which means we first perform a OR and then we perform a NOT. So what would be the Z flag in this case? It would be a 0. Very good. So, maybe there is something useful after all, because in this case, the sign flag is going to be a 1, the Z flag is going to be a 0. Okay? You might ask, but why do we need to know about the sign flag or the 0 flag? Well, that's applicable in today's lab. Okay, so I'm only giving you bits and pieces. I will leave it up to you guys to make the connection because that is the most important part of taking a class is the connection. Then you go like, but aren't you supposed to be the person giving us all the connections? No, I'll give you points that are close enough so that you can make the connection. Because if I give you the connection, I almost guarantee you that most people will not remember that the moment they walk out of the lab. But if you make the connection, it'll stay with you for a long time. Even when you think that you have forgotten the connections, you go like, wait, hold on a second here. I know this. All right. Are we okay here? So then you look at and AA, then you look at or AA. You go like, isn't that going to do the same thing? Because if I were to repeat this whole thing, okay, there are 1, 2, 3, 4, 5 lines, and just repeat the whole thing here, you go like, oh, but it's going to do the same thing, even though this is a bitwise or, it's going to do the same thing because 0 or 0 is 0, 1 or 1 is a 1, 1 or 1 is a 1, 0 or 0 is a 0, etc. So I go like, we just need to keep one of them. Okay, the other one does not need to be kept. Okay, so what I'm doing here is I'm trying to identify things that are useless. So of these two, okay, I'm just gonna use a little symbol here. One of these two does is useless. Useless as long as we have the other one. Okay. So now the question is, which one are we keeping and which one are we going to hijack? Okay. So hijacking means we're looking at a certain opcode that would otherwise be doing something senseless like this, and we go like, we're going to reuse that opcode to mean something else. That's what the term hijacking means. So now the question is, what does compare AA or CPR? Sorry, what does copy register AA look like in terms of opcode? Don't ask me. I don't remember. I really cannot remember. So what I need to do is to go to the opcode table and go like, oh, okay. So if x and y are the same, they're both register A. That means x is going to be 0, 0. Y is also going to be 0, 0. The opcode is going to be 5, 0 because 0, 1, 0, 1 is a 5. And then we have 0, 0 for x, 0, 0 for y. So it's 5, 0. They go like, okay, so that opcode is useless. It can be used for something else. What something else are we talking about? So now you have to look through all the opcodes that start with 0101 and see if there's another one that is doing that. And apparently I have not overloaded or hijacked this particular one. Let's pick another one. Let's pick compare AA. Okay, so going back to this code here, going back to this page, compare AA is also useless because the outcome is always going to be the same. So why would you want to do that if you already know what the result is going to be? So compare AA is, I'm looking for the compare operand here. Compare is right here. Okay, this is the one we are looking at. So compare AA would have been E0, okay, because 1110 is E, and then XX is going to be 0, 0, YY is going to be 0, 0 when we compare A to A. So we are looking at E0 and ask, is there any other code here that it has the same opcode? Because this opcode is useless to us. We can repurpose or overload it to do something else. And we go like, wait, hold on a second here. This one can also be E0 because in this case, XX, XX are the same. In other words, whatever the first XX is, the second XX also has to match the same pattern. So that means, as far as the assembler is concerned, CMP AA and decrement A would compile to or would assemble to exactly the same opcode. Somebody from yesterday's class asked a very smart question. So in that case, would it actually compare A to A or would it actually decrease the value of A by 1? The answer is it decreases the value of A by 1 because decrement X is the one hijacking compare XY. Is that okay? So this is what I mean when I said, this opcode is being hijacked to do something else because a certain combination of certain opcode does not make sense. Can we do it? Yes, we can definitely compare A to A, but why would we do it? Because it doesn't make sense. So that's why if the compare AA opcode, when XX and YY are the same, it would actually do that. Is that okay? Now, this is particularly important in today's class, okay, because from what I saw yesterday, a bunch of people try to put in, compare, something to something, that does not make sense in the code. Okay, so now you know that compare a register with itself will never work because it becomes decadent. Are we doing okay with this? Okay, all right. So one more thing I do need to kind of talk about is, okay, there's increment. So increment, you can, if you see XXXX here, it means it is hijacking somebody else. So can someone tell me what increment X is hijacking from?
Or,
Hmm?
or,
Yep. So that's why your OR AA actually does not do what OR AA is supposed to be doing. It would instead increment the register. Very good. Okay. So that particular one, you'll answer like another specific question in today's lab. You might want to write it down, or is hijacked by increment X. What about AND? Do you think AND is hijacked? It starts with 1100. So you just look at all the other opcode and say, okay, who else can start with 1100? Nobody. So that means AND is not hijacked. AND always does what it is supposed to be doing. So AND AA would actually do a bitwise AND between register A and register A, and then use the result to update, guess what? Register A. A otherwise useless operation, other than it would also set the flags in the flags register. So AND AA would still do this, but OR AA, it does not exist. So this cannot really happen in this processor. All right, so I have given you a whole bunch of um, in, pieces of information. The last one is this, okay? It's not A, okay? This is an actual mnemonic, okay? If you can execute it. So assuming that A has a content of 10010110, then the result of this, okay, the negation of this is going to be the same as a tilde, because that's the bitwise and bitwise not operator. So the result of this is just flipping all the bits, so that a 1 becomes a 0 becomes a 1, like that. What does that remind you of? In other words, I'm trying to help you make connections to concepts that we have learned already. When did we encounter this operator, the tilde operator? Yes. Yes, this is one of the things you need to do in order to compute 2's complement. This by itself is the same as 1's complement. Yeah. If you add 1 to the result of this, then you have 2's complement. And why do we do 2's complement? What does it do actually? Yep.
for a positive number to a negative number.
Yep. It performs a arithmetic negation. Yep. That's going to be needed for today's lab too. So, all of these are pieces of information that you need. The only question is, how do you put all of these things together when you're answering the questions of today's lab? Today's lab has a second component where you have to upload the program. So the program needs to be in a text file. So let me show you what I mean by a text file. So this one, this is a text file. Okay, I have to comment this out. So this one is a text file. It only contains instructions that we know. Oh, I take it back. Somehow I didn't save it. Wait. Hold on a second. Is this the file that I worked on today? Okay, let me double check. v3.ttpasm. Yep, this is the one that I worked on today. And it still has d equals c. Did I save it to the wrong file? I think I might have saved it in the wrong file.
Isn't it 3B?
Hmm?
3B?
3b is a .c, so I might have overwritten 3b. Okay. I will do. I changed the wrong file. But the fingerprint is still left over as comments. So we can still track back of how we changed the file. Just that was not the intention. But anyway, this is the kind of text file that I want you guys to turn in. It is a simple text file that has mnemonics in it. So I don't want you guys to turn in a CSV or a TSV file. I don't want you to turn in a RAM file. I want you to turn in a file that has mnemonics as instructions. So that's the second part of today's lab. The lab should have released itself automatically depending on what the current time is. I'm looking at the time. Okay, it is after 11:50. So I think the lab is automatically released already. You guys can give it a try. It is ABS. The access code is ABS. So just ABS, all lowercase for absolute value. So can you guys get into it? Okay, excellent. So you can get started with this one. Okay, I'm going to upload, I will stop the recorder now and upload the